Wow, it's really kind of wild how fast everything is changing in AI these days, you know? Keeping up can feel like a job in itself.
Yeah, definitely.
But hey, that's why we're here to kind of cut through all the noise and bring you the stuff that really matters, like the core insights. And today, we're diving deep into a paper that's been causing quite a stir in the AI world. It's called Situational Awareness, The Decade Ahead by Leopold Aschenbrenner.
Right. This paper came out in June of 2024, and honestly, it's a pretty fascinating attempt to figure out where AI might be headed, like, over the next few years.
It's one of those thought-provoking pieces you come across. So where does this paper get its information?
Well, it's a mix of stuff, really. You've got publicly available data, then Aschenbrenner's own thinking and analysis.
Okay, so he's not just pulling this out of thin air.
No, not at all. And he's also tapped into, a network of knowledge within the AI field.
Oh, so he's spoken to some of the big names in the field then?
Absolutely.
Yeah.
In fact, he dedicates the paper to Ilya Sutskever and acknowledges insightful conversations with a lot of other key AI figures.
So we can be confident that this is serious stuff.
Oh yeah, definitely some heavy hitters. Gives you a sense of the weight behind it,
Exactly. And whether you're just starting to dip your toes into AI or you've been following it for a while, this deep dive is for you.
That's right.
We're aiming to make this accessible for everyone.
Yeah.
We want to pull out the big ideas, the most important arguments, and make it all clear and easy to understand.
Definitely.
Basically, by the end of this, you should have a good grasp of where AI could be heading by 2030, according to this paper.
Exactly. And to get to that point, we need to start with the paper's central thesis.
Right. Lay it on us.
Well, Aschenbrenner argues that we could see artificial general intelligence AGI, that is, as soon as 2027. And that's AI that can do basically anything a human can intellectually.
Wow. 2027. That's not very far off. And what happens after we achieve AGI?
Well, he suggests an intelligence explosion could follow, leading to superintelligence. And get this, he thinks a small group of people, mainly in San Francisco and in top AI labs, are already seeing the signs pointing to this future.
That's fascinating. So let's unpack this. The first part of the paper is called... What's the main argument here?
Well, the core idea is that we can project the timeline for AGI by looking at current trends in 3 key areas. The first is compute. That's how much computing power is used to train AI models.
Right, so bigger models, more computing power.
Exactly. And the second is algorithmic efficiencies, or how well the algorithms themselves are improving.
Okay, so like smarter algorithms, basically.
Yep. It's not just about brute force, it's also about cleverness.
Makes sense. And the third area?
The third is what he calls unhobbling gains, basically. Ways to unleash the potential that's already in these AI models.
Interesting. So like taking the training wheels off and letting them go full speed.
Yeah, something like that. And to measure progress in all of this, he uses this concept of ohms, orders of magnitude.
Okay, ohms, that might sound a bit technical. Can you break it down for us?
Sure. Think of it like this. 1 ohm is a 10-fold increase. So 2 ohms would be 100 times bigger, 3 ohms would be 1,000 times, and so on.
Got it. So it's a way to grasp how fast things are scaling up.
Exactly. It's all about scale.
Okay, so back to GPT-4 and AGI, where do the ohms come in?
Well, the paper looks at the leap from GPT-2 to GPT-4, specifically the compute used for training.
Right, GPT-2, wasn't that a few years ago now?
Yep, came out in 2019. It was trained with around 4 E21 FLOPs, which is, well, it's a measure of computing operations.
Yeah.
By 2023, GPT-4's training compute was somewhere between 8 E24 to 4 E25 FLOPs.
Wow, I don't even know what those numbers mean.
Basically, that's about a 1.5 to 2 order of magnitude increase, meaning they scaled up the compute by something like 100 to 1,000 times.
Okay, that is a huge jump in just 4 years. So that's the first driver just throwing more computing power at the problem.
Right. But it's not just about bigger machines. These algorithmic efficiencies you mentioned, they're super important too.
So how have the algorithms themselves been getting better?
Well, it's how effectively they can learn from data. And the paper argues this progress is just as important as raw compute, but harder to measure.
Yeah, that makes sense. It's less visible.
Exactly. But to give you an idea, Aschenbrenner looks at this benchmark called math. It's a set of tough high school math problems. The compute needed for 50% accuracy dropped by almost 3 ohms in just 2 years.
That's 1,000-fold reduction. So that's 3 ohms of algorithmic efficiency gain right there.
Exactly. And the trend suggests it's been improving by about half an ohm per year.
Wow. So even if we kept the compute the same, they'd still be getting way better just from algorithm improvements.
Right. Though, of course, they're not keeping the compute the same. It's going up, too.
Of course. So how much did the algorithms improve between GPT-2 and GPT-4 then?
It's hard to say for sure. It's kind of like a trade secret. But based on things like API pricing, he estimates it was probably 1 to 2 OMs worth of algorithmic efficiency gains.
Okay, so a decent chunk of GPT-4's improvement is actually from smarter algorithms, not just bigger computers.
Exactly. And he projects another 1 to 3 ohms of improvement in algorithms by the end of 2027.
Okay, so it's like a 1-2 punch, bigger machines and smarter software. That brings us to those unhobbling gains. What exactly are those?
It's like this. Imagine you've got this super smart AI, but it's kind of held back. It's not using its full potential. Unhobbling is about removing those limitations, letting it shine.
Okay, so these are ways to unlock the existing intelligence without necessarily making the model itself bigger.
Yeah, that's the idea. And often these are low compute tweaks, but they can make a huge difference.
Give us some examples, like how are they unhobbling these models?
One big one is reinforcement learning from human feedback, RLHF.
Oh yeah, I've heard of that. It's about making the AI's output more aligned with human values, right?
Right. It's often discussed in that context, making the AI less toxic.
Yeah, to prevent it from going off the rails.
Yeah, exactly.
Yeah.
But RLHF, it wasn't just about making the AI nicer, it also made them way more useful.
Really?
The Instruct GPT paper showed that a smaller model trained with RLHF could beat a much larger one that wasn't trained with it. Mm-hmm. It's kind of like you're giving them a better instruction manual, you know?
So it's more about giving them the tools to apply their knowledge effectively, not necessarily making them smarter in a fundamental way.
Exactly. It's about refining their behavior.
I like that, refining their behavior. It sounds very polite for an AI takeover.
Yeah, well, we'll see about that.
True. So what other tricks are there for unhobbling these models?
Another really cool one is chain of thought prompting, or COTI for short.
Okay, SOTI, and what's that all about?
It's surprisingly simple, actually. You just prompt the model to, think step by step when solving a problem. And amazingly, this can be like a 10x boost in performance, especially on math and reasoning tasks.
So it's like encouraging the model to show its work.
Yeah, exactly. It's almost like they're thinking out loud, which somehow unlocks a whole new level of performance.
So just by changing the prompt, you get this huge improvement. Amazing. What other techniques fall under unhobbling?
Well, there's scaffolding. It's like you have multiple AIs working together, each with a specific role. One might plan, another proposes solutions, and a third critiques them,
So it's like a team effort.
Right. And this has worked really well, especially in areas like coding. There's this system called Devin. Yeah, the Devin AI agent. It uses scaffolding and some other techniques to get significantly better results on those programming benchmarks than even a standalone GPT-4.
So it's all about orchestration, figuring out how to leverage the strengths of different AI components.
Yep, it's teamwork makes the dream work, even for AIs.
It seems like a running theme with these unhobbling games is just finding these really clever ways to use the intelligence that's already there.
Absolutely, like giving them access to external tools.
Tools? What kind of tools?
Think web browsers, code interpreters, things like that. It basically lets them go beyond their training data and get more info.
So they're not just stuck with what they were initially trained on.
Nope. And another one is increasing context length. How much info the model can process at once. We've gone from 2,000 tokens in GPT-3 to over 1 million in models like Gemini 1.5 Pro.
Wow, 1 million. And how does that help?
It's a huge efficiency boost. Think of it like this. If you could only read a couple of pages at a time, it'll take you forever to learn something complex. But if you can read a whole book at once.
That makes sense. Like a human reading a long document, you get the full context.
Exactly. And we've also seen significant post-training improvements in models like GPT-4.
Post-training. So they keep tweaking it even after the initial training.
Yeah, and it's led to big gains in things like reasoning.
So it's like they never really stop learning.
Pretty much.
So when you add up all these expected gains in compute algorithms and those unhobbling techniques, what does Aschenbrenner think will happen by 2027?
He thinks we'll see another big leap in capability, something comparable to the jump from GPT-2 to GPT-4. We might have models that can do serious AI research and engineering themselves.
Okay, so we might have AIs designing even better AIs. That seems like a bit of a feedback loop, wouldn't it?
Exactly. It's a key step on the path to AGI.
Now, one thing that always comes up with these huge models is, do we have enough data? won't we hit a data wall?
Yeah, that's a common concern. If we just keep feeding them more and more internet data, will they eventually run out of stuff to learn from?
Exactly.
Aschenbrenner acknowledges that, but he's optimistic we'll find ways around it.
What makes him so optimistic?
Well, he points to a few things, like how humans can learn a lot from just a few well-written textbooks. So maybe we can improve the sample efficiency of AI training, get more knowledge from less data.
Makes sense. We don't need to learn everything. We can focus on the most important stuff.
Exactly. He also talks about bridging the gap between pre-training and in-context learning, which could lead to more efficient learning.
Okay, and remember AlphaGo.
Yeah, Go playing AI.
That was a great example of how they got around limitations, right? It wasn't just about feeding it data. It learned through imitation and self-play.
Exactly. AlphaGo shows that clever training can overcome those perceived limitations. And with all the focus and money pouring into AI research, Aschenbrenner thinks the data wall isn't going to stop us from reaching AGI.
Okay, so that's a pretty compelling case for AGI being within reach in the next few years. But the paper doesn't stop there. It goes on to discuss what might happen after we hit AGI. And that's where things get really interesting, right?
Yeah, it gets pretty intense. The second part of the paper talks about the intelligence explosion, which could lead to superintelligence.
That's a pretty loaded term, intelligence explosion.
It is. The idea is that once we have AGI, it can start automating and speeding up AI research itself. We could have millions of AGIs working around the clock at speeds we can barely imagine.
Wow.
And that could compress decades, maybe even centuries, of progress into just a few years, or even less.
That's insane. But if AIs are designing AIs, won't that just accelerate things even faster, like a runaway train?
That's exactly the point. This runaway effect is what they call the intelligence explosion.
Yeah.
And it could lead to AI systems that are vastly smarter than any human.
Okay, now I'm getting a bit nervous. But to be fair, haven't people been talking about superintelligence for decades? Why should we take this seriously now?
Well, the paper uses a pretty powerful analogy to explain why this time might be different. It compares the transition from AGI to superintelligence to the difference between the atomic bomb and the hydrogen bomb.
Oh, wow, that's a big jump.
Exactly. The A-bomb was revolutionary, but the H-bomb was orders of magnitude more powerful. It was a whole new level of destructive capability. And he's arguing that the jump from human-level AGI to superintelligence could be a similar kind of leap.
A qualitative change, not just a quantitative one. Okay, I see the analogy and it is a bit scary. But how exactly would these AGIs automate AI research and cause this explosion?
There are a few ways. First, they could explore the huge space of possible AI architectures much more efficiently than humans. Like, imagine testing millions of different neural network designs in parallel.
Right, they wouldn't be limited by our slow human brains.
Exactly. And they could also figure out how to allocate training compute more effectively, like which problems to focus on, which algorithms to use, and so on.
So it's like having an army of super efficient AI researchers all working in perfect sync.
Exactly. And then there's the possibility that they'll discover totally new unhobbling techniques that we haven't even thought of yet.
Yeah, who knows what they'll come up with.
Exactly. Aschenbrenner also points out that some of the current bottlenecks, like those long and expensive training runs, might become less of an issue during an intelligence explosion.
Why is that?
Well, the AIs might find ways to optimize those processes, maybe even find shortcuts we haven't thought of. And that could lead to even more sudden jumps in intelligence, like big leaps instead of gradual steps.
Okay, so it's not just a steady acceleration. It could be like a series of sudden breakthroughs.
Exactly. It's a pretty mind-blowing concept.
It really is. So it's the argument basically that once we get AGI, everything else, like robots and so on, will just sort itself out.
Well, he does think that the actual job of an AI researcher is pretty automatable.
Sure, it's a lot of thinking, experimenting, coding, all stuff an AI could theoretically do.
Exactly. And while robotics and the real-world rollout might take longer, the core research part, he thinks, could see an explosive jump.
Okay, so even if the robots aren't there yet, the intelligence explosion could still happen in the digital realm.
Right.
He also mentions this idea of thinking out loud, that chain of thought technique, as a possible way for AGI to understand and improve its own reasoning.
Yeah, it's like they're introspecting, reflecting on their own thought process.
Right, but he doesn't think that'll be the main way forward, does he?
No, probably not.
Ah.
But it's interesting to think about. And it's important to remember that the impact of superintelligence wouldn't be limited to AI research. It could lead to crazy advancements in, well, pretty much everything. Medicine, energy, materials, science, you name it.
Yeah, if they can automate science itself, who knows what's possible? And what about this argument that robots will be the limiting factor, that superintelligence will just be trapped in the digital world? What's his take on that?
He used to think that, but now he's more convinced that robotics won't be a major long-term barrier.
Really? Why is that?
He thinks the fundamental problems with robot hardware are being solved pretty quickly.
Okay, so the robots are coming, along with the superintelligence. Great.
Well, the point he's making is that the intelligence explosion is something we need to be prepared for, and that it could happen sooner than we think.
Definitely getting that message loud and clear.
Yeah, this whole section emphasizes how volatile things could get, how unpredictable, and the potential dangers of this transition to superintelligence.
He compares it to those early discussions about nuclear chain reactions, where people weren't sure what the consequences would be.
Exactly. It's that same kind of feeling of the unknown. So yeah, it's a pretty wild ride, this intelligence explosion idea.
Absolutely. All right, so we've covered the path to AGI, the potential intelligence explosion. But now let's talk about the challenges, because I'm sure there are many. And the first one the paper dives into is pretty daunting, racing to the trillion-dollar cluster.
Yeah, that title alone gives you a sense of the scale we're talking about.
Trillion-dollar clusters, what does that even mean?
Basically, he's talking about the cost of building these enormous AI training facilities, the hardware, the energy, the whole shebang. And it's going up fast.
Right, because all this AI progress isn't cheap.
Definitely not. And this section highlights the massive acceleration we're seeing in tech investment, all driven by the huge growth in AI revenue. Aschenbrenner estimates that big tech companies could be raking in $100 billion in AI revenue annually by 2026.
Wow. $100 billion per year? That's insane.
Yeah, it's mind-boggling. And by 2027, the total annual investment in AI could be north of $1 trillion.
$1 trillion? That's more than some countries' entire economies. And where's all that money going?
It's going to fuel these increasingly massive and powerful AI training clusters, those trillion-dollar clusters he talks about.
So these clusters, they're basically like giant AI brains.
Yeah, you could think of it like that.
And just how big are we talking here?
Well, he predicts individual clusters costing hundreds of billions of dollars by 2028, potentially even hitting $1 trillion or more by the end of the decade.
Okay, $1 trillion. What would $1 trillion AI cluster even look like?
Well, imagine a facility the size of a small city, filled with rows upon rows of supercomputers, all crunching numbers and training AI models.
Like a server farm on steroids.
Yeah, exactly. And the energy demands would be staggering. He estimates that $1 trillion cluster by 2030 might need more than 20% of the entire electricity production of the U.S. right now.
Wait, 20% of all the electricity in the U.S. just for one of these things?
Yeah, that's what he's projecting, based on current trends. That's like needing hundreds of nuclear power plants just to run a single massive AI training session.
That's hard to wrap my head around. Does he lay out how much this will all cost and what's needed in the paper?
He does. He has this whole table where he projects out to 2030, showing how these clusters could grow in terms of cost, power consumption, and the number of AI chips they need. And he points out that NVIDIA's recent crazy growth in data center sales, that's just a tiny taste of what's to come.
So this is just the beginning. But can we even handle that much energy consumption? Wouldn't that, overload the grid?
That's the biggest challenge he sees. He calls power a binding constraint. Basically, the biggest bottleneck to building these huge clusters.
Right, because even if we could build them, we might not be able to power them.
Exactly. And building new power plants, especially the reliable kind like nuclear, takes a long time. We're talking a decade or more.
So we can't just flip a switch and get all that extra power.
Nope. He even suggests that tech companies might try to buy up existing big power users, like aluminum smelters, to get their hands on those energy contracts.
Wow, just buy a whole company for their energy contract. That's commitment.
It shows how serious this is becoming. But it's not all doom and gloom. The paper does talk about natural gas as a potential solution, at least for the U.S.
Oh, yeah, right. We've got a lot of natural gas here, don't we?
Yeah, especially in those Marcellus and Utica shale formations. He does the math and suggests that powering a 100 gigawatt AI cluster might only take up a small fraction of current U.S. natural gas production.
And we could ramp up production pretty quickly, right?
Exactly. Drill more wells, get more gas flowing.
Okay, so maybe power isn't as impossible as it first seemed. But what about the actual chips, the AI brains themselves? Is there enough manufacturing capacity to build all those?
That's a good question. While chips are often the first thing people think of when talking about bottlenecks, Aschenbrenner argues they might actually be less of a problem than power in the long run.
Really? Why is that?
Well, right now, those advanced AI chips are a pretty small part of what companies like TSMC can produce. So there's a lot of room to ramp up production.
Okay, so there's potential there.
Yeah, but there are some near-term challenges. Things like advanced packaging technologies and high bandwidth memory, they're going to be key for performance. We'll need to scale up the production of those components.
Right, so it's not just about the chips themselves, it's about all the little bits that make them work. And building new chip factories, those gigafabs as they call them, that takes time and money too, right?
Absolutely. They cost tens of billions of dollars and take several years to build.
So if we want to meet the demand for all these AI chips, those chip manufacturers are going to need to step up their game.
Big time. And then there's the whole CHIPS Act, the government initiative to boost domestic chip manufacturing.
Right. I remember hearing about that. What's his take on that?
Well, he thinks having more chip production in the U.S. is definitely good, but what's even more important is where those AGI data centers are located.
So it's not just about who makes the chips, but who controls the AI brains.
Right. Exactly. It's like the difference between having the raw uranium and having the actual nuclear weapon, you know?
Yeah, that makes sense. Controlling the technology is key.
Yeah, especially with the kind of power we're talking about with AGI.
So he's saying focus on those AGI data centers, make sure they're in the U.S., and maybe rely on allies for some of the chip manufacturing.
Right. Play to everyone's strengths, so to speak.
So it sounds like building these trillion-dollar AI clusters is going to be a huge undertaking. Lots of challenges, especially with power and chips. But in the end, he thinks it's actually doable.
Yeah, he does. The bigger question is who will build them and where.
Right. And who controls that incredible power?
Exactly.
Okay.
And he's really emphasizing that we're in the midst of this AI wake-up moment, this unprecedented acceleration in tech development. These clusters are going to be built one way or another. And it matters where they are and who's in charge.
It's a whole new kind of arms race. Okay, so moving on to the next challenge, and this one has some serious global implications. The paper calls it "The Free World Must Prevail," which sounds, well, pretty dramatic.
It is a pretty stark warning, for sure. The argument here is that whoever develops superintelligence first will have a massive advantage, not just economically, but also militarily.
Right. And we've always seen competition in technology, but why is this different?
He argues that this isn't like other technologies, where maybe one country's ahead in tanks and others ahead in planes, and it all balances out. He says that a lead in superintelligence could lead to complete dominance.
So it's a winner-takes-all scenario.
Yeah, pretty much. If one side has AIs that are orders of magnitude smarter, it might not matter what other weapons you have.
That's a scary thought. And he's saying that even a small lead, a few months, could be decisive. Why such a short time frame?
Because of that intelligence explosion we talked about. If it kicks off, even a small head start could snowball into a huge advantage very quickly.
Right, because they could use those for superintelligences to develop even more powerful ones.
Exactly.
And how would this play out in the real world? What concrete advantages would superintelligence give a country?
He talks about superhuman hacking, for one. Like, imagine AIs that can break through any cybersecurity system.
Yikes, that's a nightmare scenario.
It is. And he also mentions autonomous drone swarms, basically. Fleets of drones that can operate independently without human control.
That's straight out of a sci-fi movie.
Yeah, and not a happy one. And then there's the potential for AI-designed bioweapons.
Okay, now we're getting into some seriously dark territory. Bioweapons are terrifying enough without AIs getting involved. Does he give any specifics about how this could play out?
He does, but it's pretty disturbing, so listener discretion is advised.
Yeah, fair enough. But the point is, superintelligence would change the game completely and not in a good way.
Exactly.
So, what does he see as the biggest hurdles for the U.S. in maintaining its lead in AI?
He highlights two big challenges. The first is that China might just outbuild us. They've shown they can build infrastructure really fast, and those trillion-dollar clusters are going to need a lot of infrastructure.
Especially those power plants we talked about. It's one thing to have the money, it's another to actually build those things.
Exactly. And the second challenge is algorithms. Right now, Western AI labs are seen as being ahead, making those key breakthroughs. But the problem is security, or lack thereof.
So even if we come up with the best algorithms, they might get stolen.
He's really worried about that. He says that American AI labs are probably already compromised by China, that valuable research and code is probably being downloaded every night.
Wait, seriously? He's saying our labs are basically wide open.
That's his assessment, yeah. And he contrasts that with the level of security he thinks we need, what he calls super security.
Okay, so what would super security look like?
Think serious government involvement. Background checks, vetting, maybe even threats of imprisonment for leaking information. Robust physical security for AI facilities, the whole 9 yards.
So, like, treating AI research like top secret military technology?
Essentially, yeah.
But wouldn't that stifle innovation? A lot of progress in AI has come from open collaboration, hasn't it?
He acknowledges that, but he argues that the risk of losing our algorithmic edge to China is too great. He'd rather see things slow down a bit than have everything stolen.
Yeah, I can see his point. It's a tough balance, though, isn't it? Security versus openness.
It is. And he makes another point that's even more worrying. He says that even if we do manage to stay ahead, even if it's just by a little bit, it could actually make things more dangerous.
How so? I thought staying ahead was the goal.
Well, think about it. If both sides are racing towards superintelligence, and one side is just a few months ahead, there's less time for safety measures, for checks and balances. It could lead to a very unstable situation, a kind of breakneck AI arms race.
Right, where everyone's so focused on getting ahead, they don't have time to think about the consequences.
Exactly. And that brings us to the fourth section, the project. It's where he lays out his vision for how the U.S. should handle this whole situation.
Right, so this project, what is it exactly?
He argues that by 2027 or 2028, the U.S. government will have to step in and launch a major AGI development project.
So not leaving it to private companies anymore. Why not?
He thinks no startup, no matter how much money they have, can handle the challenges of superintelligence. The security risks, the ethical questions, the control issues. It's too big for any one company.
It's a national security issue at this point.
Exactly.
But the government doesn't always have the best track record with big tech projects, do they?
He brings up that point too.
I'm curious to hear his take on that.
Well, he compares it to how the government handled the COVID-19 pandemic and the Manhattan Project.
Oh, interesting.
With COVID, the response was slow at first, but eventually the government mobilized huge resources.
Yeah, it took a while, but they got there in the end.
Right. And the Manhattan Project, well, that shows how the government can handle these huge, complex scientific projects when they need to.
Okay,